All right, welcome back to the next video. So we're continuing from part one. So as I had said, you should have practiced these four and see, well, you can check note to see if you did it correctly. So I'm going to start with lithium oxide. All right, so as was said in the previous video, to construct a Born-Haber cycle, we start with the elements in their standard state. So we know that lithium is the metal. Oxygen is O2. There is not an oxygen atom. It's a molecule. Now we start with the direct route. Now the formula for lithium oxide is Li2O. That means we need 2 atoms of lithium. But in lithium oxide, you only have 1 oxygen atom. So again, we need to put a half in front of the oxygen. So this is what we are starting off with. 2 atoms of lithium plus half O2 to give Li2O. As you should know, this is the standard enthalpy of formation. Now for the indirect route, the first thing that we want to do is to convert the solid metal to the gaseous state, because that is how we are going to remove the electron. So the 2 atoms of lithium are going to be atomized. So we get them as the gaseous atoms now. So it was solid, now it is a gas. We did not do anything as yet to oxygen, so it will stay as half O2. Now both of these lithium atoms in the gaseous state, they can both undergo first ionization. So both of them will lose an electron. So we have the lithium ion, 2 of them, which means we have a total of 2 electrons because both of them underwent first ionization energy. Both of them lost an electron. So this is enthalpy down here. This was enthalpy of atomization. And this now is first ionization energy. Let me put first. And plus half O2 . So now that the metal has lost the required amount of electron, each of them losing 1, it's now time to atomize oxygen. So we need to get our gaseous oxygen atoms. Remember, if you look at the formula for lithium oxide, it only needs it only assign one oxygen. So at this point, we're only using one oxygen atom. So remember now it's time for oxygen to gain one of these electrons, and that is going to be first electron affinity. So it is 2 Li plus plus 1 electron plus O minus. As I said, first electron affinity, it is exothermic, but the oxygen is gaining 2 electrons. Lithium oxide consists of the lithium ion, Li plus, and the oxide ion, O2 minus. So this here is first electron affinity. First electron affinity. And this is second electron affinity. And now the final part of it, of the lattice enthalpy. Lithium ion, 2 lithium ions plus the oxide ion to form lithium oxide. And that's the cycle for the formation of lithium oxide. This part of the arrow, that was the enthalpy for the atomization of oxygen. All right, so now we're going to do magnesium oxide. All right, so magnesium, that's Mg, magnesium, Mg. The magnesium ion is Mg2 plus, and the oxide ion is O2 minus. That means before you even start the cycle, you should know that magnesium must lose 2 electrons and oxygen must gain 2 in forming magnesium oxide. All right, so let's start the process again. So magnesium being the metal in its standard state, it's a solid reacting with diatomic oxygen, O2, that's a gas. That will go to form magnesium oxide. All right. I'm going to leave out the labels for this one. So we know that this is enthalpy of formation. And then the first step is the atomization of our metal. So we should get magnesium oxide, magnesium being a gas plus, right here, this is two oxygen atoms. Well, it's an oxygen molecule consisting of two oxygen atoms, but in magnesium oxide, we only have one. So I need to put a half in front of the O2. I'd say it's magnesium plus half O2. That's a guess. Now, if we're forming Mg2 plus, it means that magnesium must undergo a first and a second ionization energy. So that's the first one. And then, so let's just start again. So you have the magnesium in the solid state. We have to atomize it, convert it to gaseous atoms of magnesium. And at this point, we have the first ionization energy. But because we're forming the 2 plus ion, it must undergo a second ionization energy to give us Mg 2 plus. Once that is done, the magnesium atom, it has lost the required amount of electron, which is 2. So now it's time to atomize oxygen. Remember, we only need one atom of oxygen in magnesium oxide. First electron affinity, oxygen is going to gain 1 electron. All right, so Mg 2 plus. For the state symbol, that's a guess. All right. So first electron affinity, that is here. The second electron affinity is endothermic. Alright, and so finally we draw our line coming down to magnesium oxide. And that's the Born-Haber cycle for magnesium oxide. Of course, this is enthalpy, the lattice enthalpy. And put LAT. Alright, so that's it for magnesium oxide. We're going to do, what was it? Aluminum chloride. No. So just to recap quickly, magnesium plus half O2 to give magnesium oxide. That's the direct route. First thing we do is convert solid magnesium to the gaseous state, that is atomization. Magnesium must lose 2 electrons, so we do first and second ionization energy. Once that is done, we atomize oxygen. We only need 1 oxygen atom. And so this oxygen atom, it is going to gain 1 electron. That's the first electron affinity, exothermic. Then it gains a second one, which is endothermic. So we have the Mg2 plus and the oxide ion O2 minus. Those will combine to form magnesium oxide. And so now we are going to move on to aluminum chloride. Right. For aluminum chloride, aluminum, it has a 3+ charge, and the chloride ion, it has a minus charge. So aluminum chloride is AlCl3. As usual, starting out with aluminum, the metal, solid. Plus chlorine. Right, so that's aluminum chloride. Now we have Cl2 here, but it must be equal to 3. So we have to multiply it by 1.5, which is the same as 3/2. So 3/2 times 2, that is 3. So this is basically saying we have 3 chlorine and we have 3 chlorine here. So remember, this is what must match up with this. All right. So we can go ahead now and start the indirect route. Again, just need to convert the atom to the gaseous state. So we have Al, which is a gas, plus 3/2 Cl2. Now, if aluminum is supposed to lose 3 electrons, it means we're going to need a first, a second, and a third ionization energy. So that's 1, 2, 3. So this will be the first, this will be the second, and this will be the third. All right, so it's Al plus the electron plus 3/2 Cl2. Remember to put your state symbols, right? And then Al2 plus 2 electrons plus the same 3/2 Cl2, and then Al3 plus 3 electrons plus 3/2 Cl2. So we are finished with aluminum now. So we need to atomize chlorine. So that's Al3 plus 3 electrons plus 3 Cl. So remember, in the previous examples, we only needed 1 atom of the negative ion, but this is AlCl3, so we need 3 atoms of chlorine. Now, as you can see, the chloride ion, it has a negative charge, so that means each of our chlorine atom will be gaining 1 electron. So it will be Al3 plus 3 Cl minus, and from there draw the line, come down, and that's it for aluminum chloride. So it is simple. You write the formula for the ions. So you see Al3 plus and Cl minus. So you know that aluminum has to lose 3 electrons. So simply convert it from the solid to the gas. Then first, second, and third ionization energy. Once it has lost the 3 electrons, you atomize chlorine and put the necessary amount. Based on the formula, it must have 3 chlorine. So we use 3 chlorine atoms. Now the charge on the chloride ion is minus, so each of these 3 chlorine atoms will gain 1 electron. Hence, it's just Al3 plus 3 chloride ions. So 3 chlorine atoms, each gaining an electron to form 3 chloride ions. That's it. All right, so let's quickly do magnesium chloride, which is basically this same thing here. I don't think I have to do that one. I will do magnesium chloride for the past paper. So it was actually in a particular year. So I will work it then. All right, so that is it for this video. If you have any question, leave it in the comment section. But remember, we will come back for part 3, where we put in the numbers for each of these and actually calculate the lattice enthalpy. Delta H here, we will calculate the energy. So lattice enthalpy, we will calculate this energy in part 3. All right, so that's it for this video.